Hi everyone, today we're going to be going over reinforcement learning for NLP. Specifically, we're going to be talking about the fine-tuning pipeline before DeepSeek came out, DPO reward models, then a simple introduction to Q-learning just to get a taste for what reinforcement learning looks like in a very simplified setting. Then we're going to get into more advanced reinforcement, model-based reinforcement learning, such as the reinforce algorithm in OpenAI's PPO. So most of what I'm going to be talking about comes from the InstructGPT paper and this reinforcement learning for human feedback paper. I'll probably link those in the description. Okay, so this is just a brief overview of the framework. So pre-training, I'm assuming you're probably quite familiar with. It's just training on predicting the next word in a very, very large chunk of data. Supervised fine-tuning is fine-tuning on a small data set of human-written responses to each prompt to try to get the model to predict those responses for those prompts. Then what we're really going to be getting into today is steps 2 and 3, that being the training of the reward model, then using the reward model to do reinforcement learning on our actual model. And here's just a diagram from the InstructGPT paper showing these steps. So supervised fine-tuning, again, we're not going to get very deep into it, but just as a brief overview, it's essentially you have these prompts as X, and you have the human written response as Y, and we're just training on these to try to increase the likelihood that the model is going to output something similar to this. Okay, so now we get more into the bulk of the talk today. So before I really go deeply into reward models, I want to just give a little motivation for why we're doing this and why we're doing this in the way that we're doing it. So essentially, what we eventually want the reward model to do is we want to be able to put a prompt into the model, get a response out, then ask the reward model to score this prompt. So we want to have a reward model that's able to take in a response and give it some score indicating whether or not it's a good or a bad response. So you might think, okay, so maybe in training a reward model, you get a bunch of responses and you have human annotators just annotate like a little score for each response. So it turns out there's a lot of issues with this approach, mainly in that humans are very inconsistent in terms of just giving everything a score independently. So if we did that, we'd probably have a lot of noise in our data. So I'm actually gonna bring up a whiteboard. I think that would be easier to explain. So documents, whiteboards. Okay, so instead of having annotators just annotate a score for each response, what we found, we being not me, I was not involved with this, what a lot of very smart researchers found is that you get a lot better accuracy when you have a prompt and you have some set of responses for that prompt. Just gonna draw it as like R1 being response 1 to response N. And you hire annotators to just rank these responses. So this turns out to be a lot more consistent, and they have a lot of framework, which was on the slide that I was showing, of all the things they're considering when ranking these responses. So these annotators are trained to like think of certain things, and you wind up with something like maybe R2 is the best, followed by R4, and so on. So now we've solved one problem. Now we've gotten an annotation scheme, which is a lot more consistent, provides higher quality data. But now we run into this issue of how do we get from rankings to a reward? Sorry, I'm doing this with a trackpad, so it's kind of messy. So we know our end goal, we want just some scalar score. And to start, we have rankings. So that's kind of what most of this section is going to be talking about. And the reason, sorry, I don't know if I mentioned the reason that we want to get a reward is because this is what we're going to be doing our reinforcement learning on, essentially. So once we get into doing reinforcement learning on the original model that we're trying to train, we're going to use this reward model to generate the reward for each response, and then use that as feedback for where to update our weights. Okay. Now I'm going to share the meeting again, hopefully. Where did it go? I guess I'll share my whole desktop. I feel like this could be chaotic, but okay, we got back. Okay. So yeah, so these are all the things that they're considering when coming up with the rankings. And then we get into the actual building of the reward model. So I'm going to be talking specifically about DPO reward models. There are different types of reward models, but DPO has kind of had the most success recently. So I think if you're only going to learn about one, it would be a good one to learn about. And how you make this model is you actually take the same model that you fine-tuned on for step 2. You're not using that exact model, you're kind of like duplicating it, and you're removing the final linear layer that maps to vocab size. So if you think about a transformer, we usually have, like, we're working in the embedding space, then the final layer is just a linear layer mapping to the vocab size so that we're outputting the logits of all the different vocabulary words. So in this case, we're going to be removing that final head, and we're going to be adding a linear head mapping to whatever scoring scheme we want to have. So we might decide that we want to score our responses between 0 and 10, and then we're just going to output like 11 different, like mapping to a size of 11 on that last linear layer. Okay, so now we're getting somewhere. Now we're able to output a score, kind of, but now we need to get into how we're going to train it based on the fact that we have annotations in the form of these rankings, and we want to train it to output a reward. So this is where it starts getting really clever. So if we have rankings of k elements, we're going to split them into k choose 2 pairs. So essentially, like, if we have 1, 2, 3, 4, 5 as a ranking, then we might have this be a pair, we might have this be another pair, we might have this be another pair, and so on. And we're going to do this for as many as we have in the rankings. And can I delete this? Yeah. Okay, nice. So we're gonna start by doing that. Yeah. Okay, I got back to it. And I'm gonna skip ahead just to kind of show what it's gonna look like. So after we split these into pairs, for all the responses, we're gonna come up with like the inputs to the model being some prompt. So in this case, who is Zhenya Milkovsky? Then we have one response. Zhenya Milkovsky is the lead singer of the Ukrainian alt-rock band Nervy. And then we have another response, which maybe was ranked higher or lower. Then we have the label being which response was ranked higher. So we have this for all the pairs. So it might not be the case that this was ranked directly higher. Maybe this one was ranked 4th and the other one is ranked 5th. So it's only like slightly better. But we're always going to have one that was rated slightly higher and one that was rated slightly lower, and then the label declaring which one is ranked higher. So once we have these pairs, we're going to be calculating this loss, which I know looks kind of complicated, but the motivation of this loss is we are trying to reward the model when the reward score it gives to the one ranked higher is higher than the reward score it gives to the one ranked lower. So as you can see in this formula, we have the one ranked higher. So this R theta is going to be the reward, in this example, between 0 and 10, given to the prompt, and YW, which is going to be the response that was ranked higher, minus the reward given to the prompt ranked lower. And this is going to be multiplied by -1. So if this reward was higher than this reward, we're going to be getting a low loss. And if this reward is higher than this reward, then we're going to be getting a high loss. And this part, if you're curious, is essentially just doing some averaging over all the different pairwise comparisons that we're considering. So for every prompt and every YW, meaning like the best response for that prompt, for that like pairwise comparison, and YL being like the worst, not the worst, but like the not best response for that pairwise comparison. We're going to be taking the expected value across all of these, and we're just going to be multiplying by this little scalar constant value. So yeah, so just to kind of make this concrete, let's say we put this into a model and it gave response 1 a 5 and response 2 a 1. Then assuming that it's a very stupid data set where this is the only pairwise comparison in the whole data set, then we're not going to be including the first term, and we're just going to be having something like sigma 5 minus 1, the negative log of that, and that's going to be equal to negative log sigma of 4. And I forget what that is actually, but I think I calculated it, and it was a very small loss. It was like 0.01 or something. So yeah, it's doing what we want it to do. If we predict the higher one, we give the higher one a higher reward than the lower one, then the loss is going to be low. I hope that makes sense. I know I can't ask questions over a video, but if you have any questions, you can ask me afterwards. Okay, so now we are going to be getting into a brief introduction to, actually it's not brief, it's quite lengthy, but an introduction to reinforcement learning. So I'm first gonna start by talking about like Q learning via some very simple examples, just to kind of get you thinking about how reinforcement learning looks in like a very simple environment before we build up, because there are some concepts that I think are easier to learn when you really break it down. So essentially, the goal of any reinforcement learning problem is to learn an optimal policy of interacting with the environment based on a reward. And we're going to have states, which are a situation that you can be in the environment. So if you're playing a game, this situation might be like the game board at the current moment. For NLP, this might be like the prompt you're given. Actions are possible moves or decisions an agent can make. This might be something like going left in a game or something like predicting a certain token. Um, Rewards are the feedback that the agent receives. So this could be something like getting a high score from the reward model or winning a game. And we're gonna talk about rewards a lot because there's kind of this issue where the rewards that you learn from don't actually come up as often as you would want. Like if you think about if you're training something to win a game and you're just doing random moves, most of those games you're not going to win, so you're not actually going to get a reward. And the same goes for NLP. So this is going to be a hot topic today. A policy is a strategy or function that determines the actions the agent will take in a different state. Um, and so policy and queue function are gonna be kind of confusingly similar. Queue function estimates the expected return from a state action pair, so it's kind of like the best action you can do in any state. And the difference between these two is if you're doing on policy learning, which we'll talk about more later, these two are actually going to be the same. If you're doing off policy, then your queue function is kind of where you're storing all like the information about like the best outcome you can get doing any action in any state. But your policy might be something different. Your policy might just be like, I'm gonna go in any random state I want, even if I know that it's not the best strategy. But yeah, we're gonna talk about all that later. So, a very simple example. So, imagine we have a card game called Choose the Lower Card. And in this card game, two cards between 1 and 10 are presented face up, and you win if you select the lower card, and you lose if you select the higher card. So, at the start, our agent has a policy to just choose a random card. And I know I said at the start, but that's actually going to be throughout the whole game. We're just defining this agent such that he always chooses a random card. And his goal is to fill in a queue table of knowledge about what the expected return is for each action on every possible state. So this queue table right now is going to look something like this. He has all these possible states, the states being the two cards that he can get. He has all the actions he can take in these states, and his expected reward right now is going to be 0 for all of them because he doesn't know anything yet about what the rewards might look like. So let's simulate one round of this game. So these are the two cards he's presented with, 5 and 8. His policy is just choosing a random card, so he's going to choose 5. So in this case, he actually gets a reward of 1 because he chose the lower card, which means we're going to need to update this initial queue table. So here is the queue learning update equation. So I know this might look a little intimidating, but essentially what it's saying is the old queue value, so like this expected reward right here, is going to become the old queue value plus then alpha, which is our learning rate, times the reward received plus gamma times then this right here controls for like the maximum future reward you can get. And we're going to see an example of that in the next example. But in this case, since our game is so simple, there's no future reward we can get. This term is just going to be equal to 0 because the maximum reward is just the same reward we got at this term. So we're really only focusing on the old Q value is equal to the old Q value plus alpha times the reward. So in this case, since we got a reward of 1, we're doing 0 becomes 0 plus 0.1 times 1, and thus we get a value of 0.1. Yeah, so I have the full equation written out here. If we have gamma of something like 0.9, we're still going to have 1 minus 1 as a value, so that's going to become 0. And yeah. Okay, so an important side note is that you may have looked at that example and saw that we're not really doing a lot of useful learning defining the state space in this way by just having the exact two cards. And this is a really good observation. If you were actually doing this type of learning to solve a real problem, there's usually a lot of feature engineering that goes into it. So, for example, you might have the states be whether or not the first card minus the second card is less than or greater to 0, right? Because in that case, you would just have two states, and you can do updates more consistently and come up with a more generalized policy on like what the best outcome is. Okay. So now we're going to go over a slightly more advanced example of cube learning. It's still very, very simple, but this one we are going to see some future states. And in case you're like kind of anxious to get to the not reward modeling, but model-based reinforcement learning stuff, this is going to be our last Q learning example. So in this example, and let's pretend that these empty cells don't exist, so you can't like go down to 1 and then go through these empty cells to get to 200. Let's pretend that the only path to 200 is through -1. So in this example, we can see that we have some agent and we have some maze of places it can go. And although the best initial award would be going down, the best overall reward would be going right twice, right? Because the first time around you get -1, but then the second time around you get 200. So your overall reward is 199. So how do we control for this and get the agent to go in the cell that has -1 in it, even though it's a worse outcome than going down? So now we're going to have to actually focus on these future reward terms. So let's pretend that we just start by simulating a whole bunch of rounds, and eventually it tries going down, it tries going right, it tries going right twice, and all this stuff. And we're going to do our first update rule after we discover each of these, which, remember, our future state term is not relevant at this point because we haven't discovered any future rewards yet. So we're essentially just doing the old value, which was 0, plus 0.1 times a reward. So for this one, we're going to get -1 times 0.1, so -0.1. This one, 1 times 0.1, so 0.1, and this one, 200 times 0.1, so 20. However, the second we fill in this top middle right column, we've discovered some interesting information for this row in the table, which is the future award for this state. So now, like, the second we discover we fill in this cell, we're actually going to do an update to the first cell in the table. So what we're going to do, so we have our old state value, which was -0.1, if you remember from the last slide, plus our learning rate, which we're going to set to 0.1. A little aside here, in case you're not really familiar with learning rates, you might think that, especially in the last example, like, why are we setting the learning rate so small when we're going to get a 1 every time we do that? So the important thing is that our agent, even though we know it, the agent doesn't know that, and the situation might be a lot more complicated, where we might not get that same reward every time we do that action in the state. So we want to only update in like small increments so that if it really is a good update, it'll keep getting repeated. and we won't like just do something really unstable if it wasn't a good update. Um, yeah, so that's a little aside on the learning rate. So back to what I was saying. So we have the old value, negative 0.1 plus learning rate times the reward, which is still -1. We haven't changed that reward, plus and then gamma, which is this hyperparameter, which controls how important future rewards are when assigning current rewards. So we're going to set this to 0.9, meaning that future rewards are almost as important as the current reward, but a little bit less important. So 0.9 times future reward, which is actually like the future Q value of the state. So it's not going to be 200, it's going to be this 20 value, which is the one that we're like the quote unquote expected reward for taking that action in that state, minus then the current Q value, which is negative 0.1. And if we do the algebra on this, we're going to get the new value to be 1.61. So we've made some progress here, as you can see. So now in our table for like the expected rewards for each state, we now have this value being quite a bit higher than the value of going down, which kind of corresponds to our instincts, right? Like if we go down, we're only ever going to get 1 point, but if we go right, even though we're starting by getting negative, we're eventually going to get 200, so it's a much better option. Okay, so now I'm going to talk briefly about off policy versus on policy. So I kind of alluded to this earlier, but we didn't really get into it. So on policy is when this Q table that the model is learning, where it describes expected actions in each state and like the best actions it can get, is gonna, in on policy, this is gonna be what the model is actually doing. So if the model, for example, has this Q table and has this policy, it's always going to be doing the thing that leads to the highest reward. So it's always going to be going here, then here, because that's what the Q table is telling it to do. However, this can be bad based on the way we fill in the Q table, because you can imagine if we're in this situation where the rook, we have a pawn here and a queen here, maybe the first iteration, it might go like way up here and it'll get a 0. It might go over here. I hope you can see my cursor. I'm not sure if you can. If you can't, that maybe I'll annotate. Hold on. Yeah, so it might go here, which isn't going to get it any points. It might go here. It's not going to get it any points. Then at some iteration, it'll go here and it'll be like, aha, I can get a point if I go here. Now I've learned that the optimal policy is going here. All the other actions lead to 0 because it was initialized with 0. Now I'm just gonna always, every time I'm in this situation, I'm gonna pick the pawn. However, as you can see, like, this isn't the optimal policy, because if we explored a little bit more, we would find that you can actually get 9 points if you go up here and you take the queen. So this is one of the reasons why on policy can be bad, because there's this trade-off called exploitation versus exploration, which is just always doing what you know to be best given your limited knowledge versus exploring more different options which might be better. And on policy can struggle with this. However, on policy is still going to be needed in a lot of applications, and it's actually what we do in NLP. So I know you might see this and think like, okay, yeah, that makes sense. We should never do on policy, but it's actually going to be necessary in a lot of cases. Then this is off policy. So In off policy, the model's actions in the policy are separate. Actions in the policy. Oh, I worded that wrong. I meant to say their like perceived table of what the best option is and their policy of what they actually do are separate. So this might look like the model just taking random actions, as in the little scenarios that I went over earlier, or it can be actions generated by a separate policy, maybe something like, okay, I'm gonna do what I learned is best, but I'm also gonna add in some like randomization terms. So it could be something similar, but slightly different than the policy it's optimizing. And this is often preferred because it can allow the model to learn like an optimal, like what to do in each state, and not get stuck in local minima. And usually when you do this, you can also store past instances in a replay buffer and learn from them later rather than making immediate updates, which is typically more efficient. And it's essentially like once you've seen a lot of stuff, you can make the update then versus just like always updating the policy as soon as you get information. Okay, so now we're going to start talking about reinforcement learning for NLP. So in this type of reinforcement learning, we're not actually going to be using like a little policy table. In this case, the model itself is the policy. And you can think about this actually kind of makes sense intuitively, right? Because if your actions are picking tokens, then the model's parameters are what's gonna tell us like which tokens to choose. So it makes sense that in some sense it is like a policy of what the agent is doing. And this is just a graph to show where we are right now. So Q learning was over here in the model-free reinforcement learning. As you can see, we actually have quite a bit of model-free reinforcement learning, but a lot of the more advanced models do actually use models, so we're going to be over here now. Okay, and here are just some resources. I might link them in the description, but basically there's original reinforced paper, which I used. I also found this guy who makes pretty good videos. I'll link his channel. And then this guy as well. Okay, so reinforcement learning for NLP, the reinforce algorithm. So this was the first big algorithm that really took off for reinforcement learning for NLP. And the reason why we're talking about it, even though it's less used today, is because it's actually very similar to the PPO algorithm, which is, I mean, it's still kind of the main one. DeepSeek did something different, which might change things, but for now, a lot of models use it. And they're very similar in a lot of the ways that PPO is kind of quirky, is specifically to correct for the mistakes. Well, not really mistakes, but sub-optimalities that this algorithm was causing. So we're going to talk about what this algorithm is, what's good about it, and what it struggles with, and how PPO solved that. Or not really solved it, but made it better. So, basically, so our fine-tuned transformer is going to output a response. The train reward model provides a score of that response. So as you remember before, we have that model where we cut off the vocab head, we add a little score head, and it's being trained to give better scores to outputs that were ranked higher. And based on this, it has now learned to, given a prompt, it's going to output a score. So yeah, so our fine-tuned transformer is going to output a response. The train rewards model is going to take in that response and generate a score. And then we're going to get a reward given like the score. The score is essentially going to be the reward for that response based on that prompt. So instead of a loss function, we're actually going to be using this expected reward function, which is usually just the average feedback across the batch. So if you have a batch of prompts and responses, and each time you're feeding it into the reward model and you're getting a reward, the expected reward function is just going to be the average of all those rewards that you got, which is going to be used to update the parameters. Okay, so first I'm going to actually, how should I do this? So yeah, I guess I'll just give the motivation. So typically when we're training models, we always think about loss. And we think about how if we have some like complex surface that looks something like this, I mean, it's probably going to be 3D. We want to just go down with respect to the derivative of the loss given the parameters. And we're essentially just going to roll down to one of these minimums by updating the parameters in the direction of that gradient where loss becomes lower. You can kind of think of it as the opposite for reinforcement learning. So instead of a loss function that we're trying to minimize based on the parameters, we're going to have this reward function, which might look something like this. And instead of rolling the ball down to the minimum of loss, we're going to be rolling the ball up to the maximum of reward. So this is kind of how you can think about like what we're actually trying to do. So this loss function, this reward function in a sense replaces the loss function. And instead of trying to go down the gradient, do gradient descent, we're going to be doing gradient ascent. So going up in the derivative of this, wait, how do I get rid of this? Hold on. Going up in the direction of this gradient. But for those of you who are paying a lot of attention, you might start thinking, what is the derivative of this reward function? I mean, is it even really differentiable? Like, we just have a constant here, and we're taking the average of that. How do we get the derivative of that with respect to the model parameters? And that is true. We don't really have a natural occurring derivative. So instead, researchers kind of just defined what the gradient of this function with respect to the parameters should be. So this isn't really something you can derive, it's just something mathematically defined, but it does make a lot of sense if you think about it. And so essentially, this derivative is defined as being the policy times the reward and the log derivative of that. So what I mean by the policy, it is defined as the probability of each token output at each timestamp. So if you think about, we have some prompt, then the prompt might be like, what would you call a furry animal that lives in a house that has pointy ears or something? And then the ideal response might be like a cat. This policy is essentially gonna be for, even if we predicted even if had like the highest probability, it's gonna be like the probability of all the tokens we could have picked in that 0th timestamp. And then for the second timestamp where we predicted cat, it's the probability distribution of all the possible tokens we could have picked. And then, so based on taking the expected value of the derivative of the log of the policy times the reward, we're going to be doing some update to the parameters. And as you can see here, whereas in gradient descent, we're usually subtracting, here we're adding. So we're going up the gradient and we're adding our learning rate times then this derivative of the reward function here, which is defined in the line above. So the common sense explanation of this is essentially if we got a good reward at the end, we want that distribution, that probability distribution of tokens, to be kind of maximized in that direction. So if we got a really good reward when we said a cat, we want those tokens to be chosen again. And we want to like go in this direction that led us to the good reward. And we want to scale this by the actual reward received, right? Because if we got no reward, then this is going to be 0 and we're going to be doing no update, which makes sense, right? Because if we didn't get a reward, we don't want to change anything. Or if we got a really high reward, we might want to change it a little bit more than we would have if we got a low reward. So yeah, so this, we move the parameters in the direction that maximizes this and scale it by the reward received. Okay, so there are going to be some problems with this. So as we mentioned before, it's on policy, right? Because we have the policy is going to be the actual model. And after each batch, based on the feedback, it's going to be updating its parameters. So by definition, it is an on-policy learning method. And as we talked about earlier, this can be kind of dangerous because if a bad policy update happens, the model's gonna update its weights to make this more likely, and it might keep going down a suboptimal path that will be hard to recover from. So this is like the NLP equivalent of learning to take the pawn instead of the queen and updating continuously in that direction, which makes it hard to recover. Big policy updates can also lead to rapid forgetting of fine-tuned data. So this is actually a lot more worse of a problem than just learning something bad. And it's because you've already poured so much money into making this huge fine-tuned model. And now if you're unlearning useful stuff, you've kind of just wasted billions of dollars on when you learn that stuff in the first place. So we also have another issue with this, and that's going to be this issue with sparse rewards. So here I have a screenshot from a conversation I had with ChatGPT where I uploaded a physics document and I asked it to explain what's happening. And this is just a subsection of the response, but as you can see, it starts by talking about the physical setup of the system, the objectives, it goes more into calculations, and so on. So let's pretend that this response got a low reward from the low reward model. Now, our policy update would tell us that all the tokens predicted, like those probability distribution among tokens, is bad. However, that might not exactly be the case here. Like, I mean, based on such a complex response, how do we really define, like, what parts were good and what parts were bad? I mean, could it be possible that this system involves an objective were like really, really great, and then it just made a small error in the calculation later on? I mean, is it possible that the inverse of that happened? And so on. So we have this issue where we are scoring an entire response, which might have good and bad parts, by a single reward. And determining the probabilities of that entire response based on just one reward. So in off-policy methods, and I'm gonna give a little disclaimer and say that there are a lot of, like, this is a huge research field in reinforcement learning. I'm not claiming that this is like the only way to do it, because many people have come up with a lot of like brilliant solutions. But one very simple way you can work at solving this in off-policy methods is you can get a lot of data by running the experiment over and over again with the belief that if certain tokens in here were actually good, they actually should have been in here, then after enough iterations, those tokens will be found in enough good responses that they'll stay high likelihood, and the parts of this that shouldn't have been here will be present in enough bad responses that those distributions will be minimized. So I hope that makes sense. It's sort of just like if you do enough iterations, even though we have this problem, it'll even itself out in the long run. However, we're not an off-policy method. We can't just simulate a bunch of different explorations of this, then combine them all afterwards and hope we end up with something that has worked itself out. No, we're actually going to be updating it as soon as we get the reward. So if we make a bad update, I mean, let's say like most 90% of this was correct and just like one error in the calculation, then we've just essentially like hindered the likelihood of getting all these other tokens, which were good. So we really have this increased risk of doing bad policy updates, which can hinder future learning. Okay, so now we're going to talk about PPO, which is OpenAI's big breakthrough reinforcement learning algorithm, and it's actually a lot simpler than it seems. So the main idea is that this reinforce algorithm, one of its major problems was that a bad update could really hinder learning. It could make it forget stuff. It could make it go in the wrong direction. And the main idea is that we're just going to make the policy updates very small. And the idea of this is that if the update was good, it'll keep repeating itself in that same direction through more epochs, eventually leading to the same outcome. And if the update was bad, it won't hinder the model too much or lead to rapid forgetting. And not only are we going to make the update smaller, but we're actually going to stop updating at a certain point where it gets too far from the beginning model, because we also want to control for forgetting past information. And if we keep training to the point where we have a model whose weights differ dramatically from the old model, then we've probably forgotten a lot of information. So you might be thinking, if we just want to make the policy updates very small, why can't we just lower the learning rate so we're not updating as much in each step? So the gradients can actually be arbitrarily large. So even with a small learning rate, like you're not really lowering the thing that's causing the magnitude, you're just kind of scaling everything by a smaller constant, which isn't going to be ideal. And I mean, this isn't precisely related to the learning rate, but another problem we have is that reinforce is sample inefficient. So basically, what I mean by that is the way reinforce works is we take in a batch of like we take in a batch of, like, you do the prompt, you get the reward based on the response, you make an update, and then you throw away all that data on the response and the reward. And the reason why we have to throw that away is because we've already done like a big gradient update on this same data. We've already used it, and we've already differed our policy enough that like the model that produced that data is going to be really different than the model we now have. So it doesn't really make sense to use that same data as if this was something our new model predicted, even though the parameters are very different now. So Yeah, that's what I just said. So what PPO is going to do is it's going to clip the gradients so that we're only making small updates that don't differ too much from the source model. And this is going to allow us to actually reuse the data. So what I mean by reusing the data is that the prompts, outputs, and reward are actually going to be collected and stored after every update. Then in a future epic, those same outputs, prompts, and rewards are going to be used with a slightly different model um, and updated in that same way. So basically, so this policy, so now we're going to have a slightly different policy. So based on the same prompt, the probability distribution across all tokens for each timestamp might differ a little bit. But the idea is that it's not going to differ so much that updating it again in the same direction would be unreasonable. Yeah, so we have a slightly different probability distribution, but we have the same prompt. So the probability distributions are going to be for the same tokens at each timestamp given that prompt. Then we're scaling it by the reward again, which was the one that we stored, then doing another update. Okay, so here is the actual PPO formula from the Instruct GPT paper. And you may be a little bit intimidated by this, but it's actually very similar to what we just saw. So this right here is the policy of the current model. And this is divided by the policy from our supervised fine-tuning model. And this is being subtracted by the overall gradient. So as you can see, if this gets too large, then we're going to be doing smaller and smaller updates the more that our policy differs from the original policy we had. And this coefficient beta is going to essentially be controlling how important this discrimination is between how different the model we have differs from the supervised fine-tuning models. And this area here, they talk about it right here. It's kind of something they did in some experiments, but I would say it's not super important. And it's essentially also adding in information about the pre-training data. So maybe we don't want to forget stuff that we pre-trained on, and based on that, we'll add in this to make it go a little bit more in the direction of the pre-training policy. Yeah, so we're going to talk a little bit about KL divergence, which I mentioned here. And it's essentially, so it's a term from statistics, and it determines how much one probability distribution differs from another. And in this case, it can be used to measure how much the new policy differs from the old one in order to prevent policy updates from getting too large. So this ratio right here is what we'd call the KL divergence. Okay, so some key takeaways. So reinforcement learning is hard, and this is something that's still true, and I feel like it's a really big field right now, and not just NLP, but in a lot of areas that use machine learning, is dealing with things like the sparse rewards problem, which is that you typically don't see rewards till the very end, so it's hard to determine what actions led to those rewards, and it can be very computationally inefficient. In regards to specifically for the models we talked about, they do still require labeled human feedback to train the reward model, which can cost money. And in regards to the reinforce algorithm more and a little bit the PPO algorithm, it can be very stable because by nature it is an on-policy method. And PPO did make it more efficient by being able to reuse data, and it added a KL penalty, which you can think of as like a way of gradient clipping in order to improve stability. So PPO did make a lot of improvements, Um, but we still have some of the same problems, and DeepSeek gave a shot at trying to solve some of these. We will probably talk about that in a future video. But for now, I think that wraps up the introduction to reinforcement learning for NLP.